and there's one other topic that we have to study. It's much, much simpler than what we did last week. And that is, suppose we have two, like normally here, we would have, so normally, we have something like an ordered pair, 2, 4, right? We know how to, in mathematics, we know what that means. It's like you have a, 2, 4, and we have a point up here, 2, 4. So that's called an ordered pair, but we can also deal with something like 2, 4, 1. That's called an ordered triple, and that would be if we had a third dimension, right? Then we'd say, we go like, maybe this would be the y-axis and this would be the z-axis, and maybe, so the point might be 2, maybe this would be the 4, and this would be the z. So this would be, x would be 2, and y would be over here. This would be 4. So we go here, and then we go up 1 unit. So we go up 1. So like up to about here. So that would be 2, 4, 1 in 3 dimensions. And these represent variables, x, y, z. But in terms of our data science, they also represent variables like your first input variable, your second input variable, your third input variable. But we have many input variables. We don't just have, 2 or 3. We have 10 or 15. So we would list them like with a long list, like 15 of them. We'd go all the way out to 15. So we wouldn't just have 3. So we might call the first one x1 and the next one x2 instead of using x, y, z because, stuck at z usually at the end there. So we'd say x1, x2, x3, all the way up to x15. Maybe we have 15. So we'd have 15. So we'd list them, a long list like that. We'd still write them in this same kind of list with commas. So that's what I'm talking about. We have our variables. We can't graph them in a 3-dimensional space because we don't have 3. We have more than 3. So we're not going to try and graph them like that. But it doesn't mean we can't list them. And we do list them. When you look at your data, you have 15 rows, right? And you see there's the first row. So that's the first list. And then you'll have another set. So you have another set of lists like that. So you do see them all the time in your Excel sheet or in wherever, Weka. So anyway, in that case, so we're really just talking about like a row of our data, but we're not usually including the last column because we're not including the class variable. So we're just talking about the input variables. So, but it's a row without the last one. Okay, so anyway, we have, say we only had 4. So we define something here where we take the product of these two, we're going to call them, each row, we're going to call it a vector. We'll call it a vector, but it's just this list. So we have a vector and another vector, and we're going to multiply them. And the way, what we mean by multiply is we're going to take the first times the first, the second times the second, the third times the third, and so on. So 1 times 5 here, 2 times 6, 3 times 7, and 4 times 8. So we get this. Okay, so we can do that. So what do we get? We get 5, 12, 21, 32, right? But we don't stop there. What we do is we add those numbers together. So we would take 5 plus 12 plus 21 plus 32. Okay, so we can do that. Very easy thing to do. You just multiply each by each and then sum up what you get. So you get this. So what do I get, by the way? I get 33, 43, 53, 64, 65, 70, right? I think I get 70. 70 maybe. Okay, so this thing, this dot, this is called the dot product, and so the result of doing this would be equal to 70. Okay, that's called the dot product of these two vectors. Okay, and in general, if you have a vector A and it has n components, not just 15, but n components, and another vector B with also n components, then what we mean by the dot product of the two is that we take A1 times B1, this one times this one, and then A2 times B2, and all the way up to the end, and add them up, which you could write like this. But anyway, that's what we mean. A dot B is this. Okay? And here's the example here, and here's another example. We get this, we get that, we get 3. Okay? So that's called the dot product. And, it's convenient to write it like this. So this just means you do each one, A1, B1, you do A2, B2, you do A3, you do all of them, and then you sum them up. Okay, that's what that means. Okay, so that's called the dot product. We also need that. So we needed this calculus, but we also need this. Okay, next, we need another thing, and this is called an S-curve or a sigmoid curve or a logistic function, whatever you want to call it. It's called an S-curve, a sigmoid curve, or a logistic function. You can call it any of those. Anyway, you can see that this curve is not exactly, we wouldn't say that it's symmetric, because symmetric means, if a curve is symmetric, I don't know how that happened. If a curve is symmetric like this, right, that's kind of symmetric, means you can drop a line down here and then fold this over and you get the same thing, but that doesn't happen here. But this has a different kind of symmetry. You can see there's some kind of symmetry here. But anyway, it's sort of some kind of symmetry. Anyway, this is the curve, and you can see that this goes, the lowest it ever gets is 0, and the highest it ever gets is 1. And it never actually reaches 1, and it never actually reaches 0. And when x is 0, the height is 0.5. Okay, and this is called a sigmoid curve or an S curve or something like that. And the formula for it is this. So it looks kind of not so simple, but it's really not very complicated, because we can just check. We're hoping that as we move to the right, as x moves to the right, that this formula should be getting closer and closer to 1. So is that true or not of this formula? That's what I want to check. If I move to the right, does it get closer and closer to 1? Well, that's easy to see, because this part here, e to the negative t, what happens to that? As t, this is t, as t gets large, what happens to this? This becomes 1, this is 1 over e to the t, right? E to the negative t is 1 over e to the t. So as t gets large, what happens to this? This gets very, very large, and so the whole thing goes to 0. So this part just goes to 0, and we get 1 over 1. So it does. It gets closer to 1, right? That's easy to see. And also, as t gets very negative, then this thing actually will get much bigger, right? And then we're getting 1 plus a huge number in the denominator. That's 0. I mean, 1 over that is 0, right? If I put 1 over like 1 trillion, right, that's very small, right? Keep going. So this is getting smaller and smaller as t gets very negative. So we see that it does appear to have these properties, and it's plausible that it has this shape. We can also, I guess we could check at 0, is it equal to 0.5? Yeah, it is equal to 0.5, because when t is 0, this is just 1. So we get 1 plus 1 on the bottom, we get 1 on top, so it's 1 over 2, which is 1/2. So anyway, this is the curve. This is the formula that generates this curve, and this is called we can call it different things. Okay, so we need that. We need to know about that. We need to be able to use that. So now we've discussed that as well. So we discussed this, and we discuss this. And I don't think there's anything else we need for mathematically speaking. How do I get this to move? Okay. Okay, so the sigmoid function is continuous. It doesn't have any breaks in it. And as x goes to infinity, the height goes to 1. Or as t goes to infinity, the height goes to 1. And the derivative has some nice properties, but I don't think we really need that. So, okay, we talked about that. Okay. Any questions so far? Pardon me. So let's go on then. We want to talk about this new algorithm called neural network. And a good data set for understanding or thinking about neural networks is the data set of handwritten digits. So, you know, when the post office, they have a problem because we write we write on our letters, we write by hand usually, right? And then they either have to read, you know, they have to have a person read each address, or if they could, they could have a machine do it. But the machine has to recognize everybody's handwriting. So just, you know, I might draw numbers differently than somebody else. And we have to hope that we could get the machine to be able to know that when I write a 5, that I mean 5, not 6 or not something else. So handwriting recognition is an important problem, just like image recognition, and it is image recognition, and that's just one important problem in data science. So most people effortlessly recognize these digits as 504192. So but it's not easy. It's just that we humans are stupendously, astoundingly good at making sense of what our eyes show us. So we have super capacity to do this. It's not that it's easy, it's that we have an amazing, in our brains, we have this capacity. All that work is done unconsciously, and so we don't usually appreciate how tough a problem our visual systems can solve. Neural networks approach the problem in a different way. The idea is to take a large number of handwritten digits like this, or maybe, but not like this, like hopefully like 50,000 or 100,000 examples of handwritten digits. So here we have like, what is this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 144 maybe, or I don't know, maybe 100 different handwritten digits here. But we want to take a data set with 50,000 and then develop a system which can learn from those training examples. So they would be our training examples. In other words, the neural network uses the examples to automatically infer rules for recognizing handwritten digits. And after we train it, maybe we could actually use it in the post office. Furthermore, by increasing the number of training examples, the network can learn more about handwriting and so improve its accuracy. So while I've shown just 100 training digits above, perhaps we could build a better handwriting recognizer by using thousands or even millions or billions of training examples. We focus on the handwriting recognition because it's an excellent prototype problem for learning about neural networks in general. Okay, so what is a neural network? So, this is what we've been doing all along, right? We take our input variables and we put it into into an algorithm. We get an output. We get a prediction, right? This is what we've been doing all along, right? We have like with the iris data, we put it in. We have, in that case, we have 4 input variables, right? We have the sepal length, the sepal width, the petal length, and the petal width. We have 4 inputs, and we put it into our into Weka, and it makes a prediction. It's an iris setosa maybe, or an iris virginica. whatever. So this is the whole data science, what we've been doing, is this picture, right? Well, back in the 40s and 50s, 1940s, 1950s, scientists were working with this thing, but they were thinking of this. They were thinking of this as like somebody's eyes, and they were thinking, how do we know what we're seeing? So we get some kind of inputs, like certain kind of light, I guess, into our eye or into the neurons in our eyes. Maybe it's not light, maybe it's kind of electricity into the neurons in our brain. And then from there, we kind of make a guess as to what we're getting. So this kind of represents actually like what's going on in the brain. So that was called a perceptron. But it's exactly what we're talking about. We put in some input and we get out an output. So a type of, this is like a neuron in the brain. They're thinking of it as like one of your neurons in your brain. So what your neurons in your brain, what happens? You have billions of neurons in your brain, but they talk to each other. And how do they talk to each other? They get some kind of input from the, there's a neuron over here, and it sends some kind of signal, and then the next neuron picks up that signal. I guess the signal is chemical, or maybe it's electrical, and then the next one picks that up, and then it kind of outputs something based on what it got here. So that's what's going. We're thinking that's what happens in the brain. So a type of artificial neuron. So this is a kind of artificial representation of that. Obviously, in the brain, it's much more complicated. Even a single neuron is probably more complicated than the way we describe it here. So this is only an artificial neuron. Perceptrons were developed in the 50s and 60s by the scientist Frank Rosenblatt, inspired by earlier work by these two guys. A perceptron takes several binary inputs. So here at the beginning, the way they were studying it, you have like sepal length, right? Sepal length is not binary. Sepal length, you can put in all kinds of numbers. Sepal length can be 1.1, 1.2, 3.7, right? That's lots of different possible inputs. But they were working on a simpler project then. They were just saying, okay, suppose we can only put zeros and ones in here, not all kinds of numbers, right? They were just beginning. So they started out with just a simple case where you can only put zeros and ones. So takes several binary inputs, there's several of them, and produces a single, and here they're only thinking about having a binary output. Like in our case, we could predict, is the person like Asahi beer, Sapporo beer, Kirin beer, Heineken beer, and blah, 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 many outputs. But they were thinking only two outputs to make it simple. Produces a single binary output. In the example shown, the perceptron has three inputs, x1, x2, x3. In general, it could have more or fewer inputs. Rosenblatt proposed a simple rule to compute the output. So, we have advanced data machine learning algorithms that we've already learned about, but this was before they had that. So he had a very simple way to decide what the output was going to be. So he introduced weights, W1, W2, these are numbers, expressing the importance of the particular input. So like, this is sepal length. Well, no, they're supposed to have binary inputs, but anyway, let's suppose this was sepal length, sepal width, and sepal and pedal length, and so on. So how important is sepal length, let's say? How important is that in predicting the output, whether it's going to be iris setosa, iris versicolor, or iris virginica? So how important is sepal length? Well, I think that sepal length has an importance of 4 as opposed to pedal length, which only has a weight of 1, an importance of 1. So he put these weights here to indicate how important these are in predicting whatever we're trying to predict. So call them weight W1, weight W2. These are real numbers expressing the importance of the respective inputs to the output. So how important are these inputs in making our guess? And we put some weights here to say, oh, you're 4 times more important than you are. Okay, so that's what we say. So we have this, the neuron's output is only going to be a 0 or a 1. So only 0 or 1 for the output. So not iris setosa, iris virginica, iris blah, blah, blah. Just like, is this a flower or not? Or maybe, is this a 4 or not? Remember, we're doing image recognition. So is this a 4 or not? Or, is this person smiling or are they frowning, right? Maybe those would be the 2 outputs that we're trying to predict. Okay, so the neurons' outputs are just 0, 1. Remember, they're just trying to do this in a very simple way back then. Is determined by whether the weighted sum is less than or greater than some threshold value. So what does that mean? Let's say we had 3 inputs. So we take the height of the end of the lip, the height of the end of the lip, and the height of the center of the lip. Those are our 3 inputs. So here you'd have a certain height, a certain height, and a certain height. And here you'd have a certain height, a certain height, and a certain height. Okay? And then we're supposed to determine, are they smiling or not? Just by those 3 numbers. Did I say that X has to be binary? Yeah, X has to be binary. So it couldn't be height. Okay, well, I guess we could say the height is either only 0 or 1. So 0 means low and 1 means high. So I don't know. I'm just making this up now. Anyway, what we're going to do is we're going to have the inputs here and we're going to have the weights here. Weight 1, weight 2, weight 3. Okay? And the inputs are going to be, I think he said binary. Let's see, is that right? Well, I think the inputs are just 0s and 1s. Let's say that's true. This is 0 or 1, this is 0 or 1, and this is 0 or 1. So let's suppose we have 0, 1, 1 as the inputs. And then the weights, remember, let's say we could have like 4 here and 1 here and -2 here, for example. Okay, so we have different weights. Now, what do we do with all of this? We multiply them. We take 0 times 4, we take 1 times 1, and we take 1 times -2. So 0 times 4 is 0, 1 times 1 is 1, and 1 times -2 is -2. And then we add up the results. So what do we get? We get 0 times 4 is 0, and we add that to 1 times 1, which is +1. And we add that to 1 times -2, which is -2. So we get 1 plus -2. So we get -1 when we take these times these, we get -1. And then then we want to know what's the output going to be. So what's the output going to be? The output 0, 1 is determined by whether this sum, which is what we just did, we just got -1. So whether that is greater than or less than some threshold value. So we'll say whenever this is, let's say, whenever it's greater than 3, we're going to output a 1. And whenever it's less than 3, we're going to output a 0. So this is -1, which is less than 3. So we're going to output a 0. If we had gotten 10 here, that would be greater than 3, then we would output a 1. Okay, that's the idea. So we have some kind of threshold here. I said, suppose if it's greater than 3, then we're going to output a 1. And if it's less than 3, we're going to output a 0. In this case, the combination I gave here was -1, which is less than 3. So we will output a 0. Okay, the neuron's output 0, 1 is determined by whether the weighted sum, which is what we did when we calculated -1, is less than or greater than some threshold value. I made up a threshold value of 3. Just like the weights, the threshold is a number, like greater than 3, right? These are numbers, the weights are numbers, and this is a number, which is a parameter of the neuron. So in other words, we decide, when we say parameter here, we mean we decide what the threshold will be. I say, okay, if it's greater than 3, then we'll output. No, I change my mind. If it's greater than 5, we'll output. So that's like a decision we make before we start using our data. Our data is here. We say, we're going to make the threshold 3. So whenever it's greater than 3, we'll predict a 1. Whenever it's less than 3, we'll predict a 0. No, I'm going to change that threshold to 5. Whenever it's greater than 5, we'll predict a 1. Whenever it's less than 5, we'll predict a 0, right? We set that up in advance, and then we start running this thing. Okay, just like the weights, the threshold is a real number, which is, okay. So in terms of, if we want to write this down, what we just said, we can write it like this. We can say the output is going to be either 0 or 1, depending on what. If it's less than the threshold, then it's going to be 0. And if it's greater than the threshold, it's going to be 1. That's what we just said. And if what is less than the threshold, if what is greater than the threshold, these calculations that we do, which calculation we do, this times this, this times this, this times this, and add them up. That's what this says. We do the x times the w, the x times the w, the x times the w, and we add them up. That's what this says. We add them up. We multiply the x times w, x times w, x times w, add them up. So if that's less than the threshold, we'll output a 0 here. If it's greater than the threshold, we'll output a 1. Okay, is this clear to everyone? And that's all to how a perceptron works. It's just like this, just what we've just said. That's called a perceptron. That's called a very simple neural network. So a neural network is this, what we just described, but this is a very simple one. We want to sort of build it up so that we can have it more complicated one. But this is the basic neural network. It's called a perceptron. When you only have one node, they call it a perceptron. But anyway, this is a perceptron, this is a neural network, and this is how it works. Does everyone follow what I said? So you might wonder, well, what's so great about this? Well, I don't know what's so great about it, but it works. What we're going to do is we're going to put a lot of these together, and it will work. You can, make self-driving cars. You can do all kinds of stuff. You can do. You can be very successful in lots of machine learning applications. This particular type of algorithm works very well, as opposed to J48, as opposed to 0R, as opposed to naive Bayes, as opposed to this one works extremely well for some reason. Okay, let's keep going. So here it is, and what we do is we don't just have one, we have 3 here. We have, and here we have four inputs. So here's x1. Let's just focus on this one here. That's like this one. So this one has how many inputs? You can see this goes into it, this goes into it, this goes into it, this goes into it. We have 5. This goes into it. There are 5 inputs into this node, right? And then we have another node, and it has also the same 5 inputs. This, 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 and this. And then we have this one. This also has 5 inputs. Here, 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 here. So we have x1, x2, x3, x4, x5. And they go here, but they also go here, but they also go here. But the weights are different, right? Because here, this goes to this node. This also goes to this node. This same x1 goes to this node, but it has different weights. This is going to have a weight here, and this could have a different weight here, and this could have a different weight here. So although the input x1 goes to all 3 of these, we'll have different weights here. So the values that go into here will be different, because this might have a weight of 1, and this might have a weight of 5, and this might have a weight of -10. So you'll have 3 different weights here, even though the same input. So you're not getting Anyway, so that's the structure. Okay, so here we have 5 inputs instead of 3, and we are allowing ourselves to have many of these nodes. So we have stuff going into here, stuff going into here, and stuff going into here. But these are still going to function the same way as this one did. We're going to have a threshold here, and if it's so let's say the threshold was 3. So if it's greater than 3, we're going to output a 0, let's say a 1. And if it's less than 3, we're going to output a 1. So coming out here is going to be either a 0 or a 1. And coming out here is also going to be either a 0 or 1. The same thing, like suppose coming out here was a 1, then coming out here is also a 1. Coming out here is also a 1. Coming out here is also a 1. Same thing here. We're going to have some threshold, and then depending on what comes in, we're going to spit out like a 0 maybe, 0, 0, 0. Okay? And the same thing here. Coming out here, you're going to spit something out. Now, of course, these all have weights as well, right? So we're going to spit out like a 1, and then times a weight, and something, and a 1 times a weight, and a 1 times a weight, and a 1 times a weight, right? So then we're going into new nodes, and then, they're going to, but everything's just the repetition of this. Okay, this is the whole thing. But we just put them together like this. And why do they put them together like this? Because this is what they imagine the brain looks like. They imagine, we have like a series of neurons here, and then they all fire, and they send information to the next layer in our brain. And then the brain picks that information up, and then they fire or don't fire, and they send out new information to the next layer. So they imagine that that's what the brain looks like. So that's what they decided to model their algorithm with. Okay, are there any questions to what I've said? Okay, so that's how we put together many of these, and we get like a very complicated network. This is called a network. We have a complicated network. And this is what's really seems to do a great job at making predictions. Okay, in the network above, the perceptrons look like they have multiple outputs. So here's a perceptron. Looks like it has multiple outputs, but it doesn't really have multiple outputs. It's still the same single output. That's what I said. So here we have a threshold, and then the output is either going to be 0 or 1. And if it's big enough, if the input is big enough, bigger than the threshold, then we're going to output a 1 from this neuron. And 1 is going to be output here, it's going to be output here, it's going to be output here, it's going to be output here. So there's not different outputs. It's the same 1. Or if it was 0, 0 would be output here, 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 and here. So it's the same 0. It's not like this could be a 1 and this could be a 0. No, it's the same number. Okay. In fact, they're still single output. The multiple arrows are merely a useful way of indicating that the output from a perceptron is being used as the input to several perceptrons. Okay, it's less unwieldy than drawing a single output line, which then splits. Okay, let's simplify the way we describe perceptrons. So here's the threshold. If the input weight, this is the input, right? Remember we said that how do we get an input to here? We take all of these and multiply them times the weight. The line that goes into here has a weight, line, weight, line, weight. So we take x1, x2, x3, x4, x5, multiply x1 times the weight here, x2 times the weight here, x3 times the weight here. So we're going to do that. And then if the result, we sum it up, and if it's greater than 3 or greater than some threshold, we're going to either put 0 or 1, depending on whether it's greater than 3 or less than 3, or whatever the threshold is. So, so here we say our condition was if this is greater than some threshold. Okay, so right now we have let me just call this S, sigma. Okay, this whole thing here is S. I'll just hit S. So if S is greater than the sum, if the sum is greater than, say, 3, right? That's what we're talking about. Then we're going to send out a 1, and if it's less than 3, we're going to send out a 0. So we can just rewrite this as if s, so s minus 3 is greater than 0, right? That's the same thing, right? You just bring this -3 to this side, and we get s minus 3 is greater than 0. So we can do that. That's all they're talking about doing. Okay, so you can just take this threshold, the sum minus the threshold is greater than 0. So if you just want to have on the right side of this symbol, if you want to have 0, you can do it like this. We can say if this is the s, this can be written like this, that the whole sigma blah, blah, blah can just be called the dot product of the weight and the x. So this is the s, and then we said we bring the threshold over to this side, so we get, and they're calling the threshold b, so it would be minus b. The threshold, this stands for b, stands for minus the threshold. So that way we can have a plus b here. The threshold was 3, then b, sorry, I don't know why this always happens, but that's this weird thing. But so if the threshold is 3, then b would be -3. So then that would be okay to put b would be -3, so this would still make sense. So anyway, we would have s plus b is less than 0, or s plus b is greater than 0, and we get the output is either 0 or 1. So this is just another way of writing what we had on the last screen, but we get to write the threshold as whether it's greater than, or we get to write that whether something is less than 0 or greater than 0 instead of less than b, some threshold. Instead of having to write less than 3 or whatever threshold, we can write less than 0 and greater than 0. So you might think, well, with this, since it doesn't really matter, you're right, it doesn't matter, but they like that better. Okay, so, okay, let's keep going. Okay, now, that's what a neural network looks like. So let's practice. Let's suppose that we have a simple neural network. Okay, so I'll say we only have 1, or let's say, no, let's have 2. Let's do this, and this, and this. So we're going to have 2 inputs, but only 1 output. Yeah, let's just try that. And here, and here. Anyway, let's just take some example here. So let's suppose that we have a simple network like this. Okay, and then we're going to have an output. And let's suppose that we don't necessarily, we're not going to stick with, we need binary inputs only. Let's just relax that condition just to make it more fun. So let's just say we have a 2 as an input and a -1 as an input. And the weights here are, let's say 4 here and -2 here, for example. I just make those up. And let's say the threshold is, let's say I'll call threshold is equal to 3. Okay, so what's going to happen? And the output here is only going to be 0, 1. Okay, so what are we going to do? How do we do this? 10, you're right.
Yeah.
Okay, I get 10. Okay, good. And then the threshold is 3, so?
So it is
it's greater
1,
than 3, but
3,
so we output 1, right?
Yes.
Well, actually, no, I shouldn't have put the 1 there. I should put the 1 maybe, because that's where I would put there could be a weight on here as well. So we could put a weight here as well. So we can have like a weight of 2. But anyway, the output is 1, like you said. So we get an output of 1. Okay, good. All right, let's try another one. Let's try another one. Let's say we have, and suppose I have a threshold equals, let's say 5. And let's suppose we have let's say a weight of 6 here and a weight of -5 here. And let's suppose we have a input here of 7 and an input here of 2. Okay, let me ask somebody else. How about Vu Tao Nguyen Kun? So what happens here? Can you tell me what happens here?
Oh, I think that is maybe 2 times 6.
2 times 6.
Plus with 7 times -5, I guess.
7 times -5, okay. Which is what?
Uh,
That's 12 plus -35. Is that 23?
23.
Okay, good. And the threshold is 5, so?
Hmm.
So we either output a 1 or a 0.
So it's 1, I guess.
We output 1 because we got over the threshold. 23 is higher than 5. We got over the threshold, so we output a 1. Now there might be a weight here, some other weight like 2 here. So we could keep going. Okay, good. So here, what did we do? We took the 2 times the 6 and the 7 times the 5, -5. Now, suppose I wrote these like I did on the about 5 slides earlier. I wrote 2, 7. Those are the 2 inputs. I call that there, and then the weights I write as 6, -5. Right? Those are the weights. So I'll call this the X, and this the W. So the X's are, this is the X, and the weights are here. So I have an X vector and a weight vector. Now we talked about doing this. What do I get when I do that? Same person.
So I will take the x1, but multiply with the w1 and plus with x2.
So we get 2 times 6, right? This times this. And then we also get 7 times -5. And then we add them, right?
Yes.
That's what we meant by the dot product. That's what we said. So isn't that exactly what we did here? Isn't that exactly what we did there?
That's exactly what we did there.
Right. So we can say that when we do this calculation, we're doing the dot product of the input vector times the weight vector, right? So we can say this calculation is just X times W. These are like vectors, call them vectors. So the X vector is 2, 7, and the W vector is 6, -5. So we can just call this calculation the dot product of the input vector with the weight vector, right? Everyone agree with that? Okay, now let's try another one. Let's try this one. Have 3 inputs. So, and let's say we have 3 weights. Let's say we have 2, -5, and 4. Okay, those are the weights. And let's say the threshold is, say, 5. Okay, and let's try some weights, some values for the inputs. Let's have we have 2 and 6 and 3. Okay, so what is the X vector? Let me ask somebody, what is the X vector? So let me ask Kabirajan. Kabirajan, what is the X vector?
Hi.
What?
I don't really know. Just 2 multiplied by 2, like plus like 6 multiplied by -5, and then 3 multiplied by 4.
Okay, yeah, you're a little bit ahead of me though. I just want to know what the X vector is.
Oh, X vector.
The X vector.
Oh, vector.
Yeah, the X vector. You're right. That's the calculation we want to do, but I want to take a step before that first.
X vector.
Okay, let me ask somebody else. How about
Okay.
Takai? How about Takai? Can you give me the X vector?
So is it 5, the one on red?
5?
Is it 5? That's
No, that's the threshold. Okay, how about Elizabeth?
Can you hear me?
Yes.
Is it I'm not sure. Is it 11? Or
No.
2?
No.
Sir, it's 263.
Is it 263?
Who said that? Well, let me ask somebody else. Let me ask somebody else. Tao Li Nguyen.
Yes, Professor.
What do you think? Yeah.
The X vector is 263 and the W vector is 2, -5, and 4.
Okay, 2, 6, 3. That's the X vector. And the W vector she just said is
2 minus 5, 4.
2 minus 5, 4. So this is the X, and this is the W. So we have 2, 6, 3, and that. Now, Kabir John said that we're supposed to do what with these? He said we should multiply 2 times 2, 6 times this, and that times that, which means what? We should do the dot product of the X vector times the W vector, right? That's gives, when I do that, I multiply this times that, and this times that, and add them up, which is what he said we should do. So we can just express all of that with this. And what do we get, by the way? We get 2 times 2 is 4, plus 6 times 5 is negative 30, and 3 times 4 is 12. So what is that? That's 16, so that's 14, right? Negative 14, right? Right, so we get negative 14, and then we have to, this is the threshold, so we have to say, is that greater than 5? No, it's less than 5. So therefore the output here would be, I'm sorry, here would be 0. Now we, as I said, we could have a weight here. So we'll have a weight there. But the output from here would be 0. Okay, does everyone follow this? Now we could have, you know, I could just make a more complicated one. Of course, it's going to take longer to do it. It's not really worth it to do this, but maybe I'll do it anyway. Let's suppose we had this picture, this, we could do that. And then we have here and here. Okay, so anyway, for this one, we're going to have 2, 4 and 2, 6. 2, 6. So that's going to be for the first node in the second layer. We'll call that node 1 in second layer, or something like that. And then for node 2 in second layer, I have what? I have same thing, 2, negative 4, but then I have different weights. So what is it? 2 times 3 and negative 4 times 2. So maybe I did this right. And then I'll get something here, I'll get something here, and I have to check it with the threshold, and that'll tell me what to do here, and tell me what to do here. And then I could do it again here. Does everyone get this? So this is how we calculate the values in a neural network. It's not hard, it's very simple. Okay? Now, one thing that we want to do is, I want to call this W something and W. So right now I need how many W's for the first layer? This is called the first layer. So here, how many W's do I need? This is one W, here's another W. How many do I need for the weights in the first layer?
Is it 4?
Yeah, I need 4, right? I need this one for here, one for here, one for here, one for here. Now I want to label them intelligently. So what I mean is I want to have a W and I have 2 indexes here so that I know which one I'm talking about. So this one here, I'm going to say it comes from the first node of the first layer and it goes to the first node of the second layer. So I'm going to call it W11. So W11 here is 2. Okay, now let's continue with this. So I want 2 here. So let's say I want to, what about this 6 here? So what is that going to be? It comes from the second node, so I'm going to put a 2 here, W sub 2, and it goes to the first node, W sub 2, 1. Okay, so this thing I'll call W sub 2, 1, where it comes from 2, goes to 1. So that's equal to 6. Okay, and then I'm going to have another one, so here and here. So this is going to be, let's say, this 2 here. What's that? That comes from 2 and goes to 2. So that's W sub 2, comma 2. And then we need one more. W sub 2, comma 2 is equal to 2. And then we need one more. Which one did I leave out? This 6 I did. The 2 I did. The 3 I didn't do yet. This one here. So what's this one? What are the subscripts for this one? Can somebody tell me?
I think it's W first second.
W1,
Yes.
2, right?
Two. Yes.
So the W1, 2 is equal to 3. So now we have an intelligent way of labeling things. You know, we say, so if we had a more complicated network like this weight here, let me make it a different color. Because I want to know this weight here. So what would that be called? W's of what?
3, 4.
3, because it comes from the third in the first layer, or the layer to its left, and 4 here. Okay, so we'll use that for labeling so that we know what we're talking about. Okay, so now we know how to calculate with a neural network. Now we could do, we could do this with the iris data, right? Iris data, there are how many inputs? We have sepal length, sepal width, petal length, petal width, right? Do you remember that? And, we could have as many nodes in here as we want. We could have 1, 2, 3, and we could have more layers here. Obviously, I don't want to do too many calculations. So, but I could have a whole, a layer with 10 nodes here, and a layer with 20 nodes here, and a layer with 5 nodes here. I could keep going forever, but I don't want to do that. So I'll just put these. That's all. So okay, so the numbers for let's see, this could be sepal length, sepal width, petal length, petal length, and petal width. And these, these could be numbers like 2.2 and 3.1 and 4 and 4.2, whatever, numbers like that. And then we're going to have the weights. So it's going to look pretty complicated. And we're going to have to get weights for each one of these, which obviously I don't want to do. How many lines are there here, by the way? 12, right? We have 3 times 4, 12 lines. I don't want to label all those, but just tell me right here. What do I call that weight? What is that? W what? Let me draw it carefully. I'm talking about this weight.
Is it 1, 3?
Yeah, it's 1, 3. It's going from 1 to 3. So it's 1, 3. So W13 has a weight of 7. Okay, so we're going to have a lot of weights here. I don't want to write them all down, but you can see, right? And then, we're also going to have weights here. These are not so many. Maybe we could say, how about if I had a 6 here? What's that? 6 is equal to what? W what? We're going to do one more thing here. So these weights, we talked about this one, this one, this one, and this one are here, 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 and here. But we have to say what layer they're in also, because we're going to have weights over here. So the layer we put up here. So this is layer 1, layer 1, layer 1, layer 1. Okay, so up here we put the layer. So these are all in layer 1, but here, this is layer 2. So we have, this one goes from 1 to 1, W11, and that is in layer 2. Okay, so this one is equal to 2, right? Here's a 2. Okay, and then this one, this is called what? W21, and this is in layer 2. Okay, so that is equal to what? To 1. This value here is 1. Okay, so anyway, we'll use this notation. This means the layer. Layer 1, layer 2. If we had more layers, we would do that. All right, so that is how we calculate neural networks. So we know how to do it now. So when you go to Weka and you choose, we can choose so many different algorithms, but one of them is called multi-layers perceptron. Multi-layer perceptron. That's what we're talking about. These are called multi-layer perceptrons, also called neural network. But you can see why they're called, we said what a perceptron is, so you can see why these would be called a multi-layer perceptron. So this is a multi-layer perceptron. You can go to Weka and put your data in, and you're putting it into something like this. And actually, if you double click on the algorithm, you can choose how many layers you want and how many nodes. These are called nodes. You can choose well, not how many. You don't choose this usually. Weka will choose this for you depending on your data. But you can choose here how many nodes, and you can have many layers, and how many nodes are in each one. You can choose that in Weka. I think so. So you can, and then you can run your data through there, and that's all it's doing, what we've just been doing. Okay, basically it's a bunch of dot products. Now I left, well, yeah, that's right. But we had the threshold. We have some threshold also. So, but that's basically what it's doing. Now, but the question now is, how does the network learn? Like you see that you can take your data here and you set up all these weights, and these weights are set at random. So you must be thinking, when I say these weights are set at random, you must be thinking, well, how can this make a decent prediction then? Right? We're trying to predict, like, we're trying to predict, is it an iris setosa, an iris virginica, or is it an iris versicolor? So you're thinking, well, you're going to put random weights here, and then maybe somehow decide, depending on the size of the output here, is it this, or is it this, or is it this? Well, you say, you can't make predictions based on that because this is all just random. How is that going to work? It's going to be completely useless. There's no intelligence here. It's just going to spit out some random number. How is that possibly going to be intelligent and make an intelligent prediction? Does everyone understand what I'm talking about? This doesn't really seem like it's, I mean, we understand how it's making the calculations, but it doesn't seem like it's doing anything. There's no intelligence. Like when we learned about J48, we sort of learned how it kind of makes decisions and so on. But here, this is just stupid. We're just calculating some random number, and how, what good is that going to do in terms of making a good guess? Well, what we've learned so far is only how it pumps out an answer, but not how it learns. How does it learn? We didn't talk about that. That's when we're going to need the derivative stuff that we talked about last week. In other words, what we're going to do is we're going to have a network. Okay, so we're going to have a network, and it's going to pump out, let's say we wanted to pump out the size of price, a stock price. So it's going to be a number. So it's going to, we're trying to predict stock price. So it's going to be a number here. So this is going to represent what the neural network thinks this price of Apple stock is going to be tomorrow. So, I think this, the neural network says, I think the stock is going to be 950 tomorrow, the price. Okay, but actually the price turns out to be not 950, but 900. So our network made a mistake here. It made a mistake of $50. Okay, the question is, how does our network learn from its mistake? Just like, we use training data, and the network learns from the training data. Well, this is part of our training data. So how does it learn? What does it do? Well, what's it going to do? Anybody have any idea well, remember we have all these weights here, W11 and W31 and all this stuff, right? We have all these weights and all these weights. And I said those weights initially are randomly set. So we're going to put like a random number here, like 0.2 and 0.3, and all these numbers are going to be random at first. And so they're going to produce a random prediction, which is not going to be good for predicting the price of Apple stock. But tomorrow, we said we predicted that, but the actual price was that. So we know that there was an error of 50. What we can do is we can use the error and try and adjust the weights. So what we can do is we can try and adjust the weights so that given that same input that predicted the price was going to be 950, if we change the weights so that maybe it would actually predict 900. So somehow we want to adjust the weights based on the fact that we got some $50 error. So we try and figure out, well, how can we change the weights so that our prediction would have been not 950, but would have been 900. So, we might change this one by a little bit and this one by a little bit and change all of them by a little bit. And then, maybe that it will predict 900. The question is, how do we figure out how to change these so that it would have predicted 900? Like there are many different possibilities, right? I could change this one by 4 and this one by 3, and maybe that would give 900. But I could change this one by 5 and maybe this one to 2, and maybe that would also give 900, right? So there's so many different choices for how I could change the weights to get the 900. So we don't know what's the best way to change the weights to get the 900, but that's what we do. We change the weights based on the error. So we got an error of 50, then we change the weights somehow so that the error wouldn't have been as big as 50. And then we do a new day, we make a new prediction, and maybe this time the error is 40, and then we go back and we change the weights again here so that error wouldn't have been as big as 50. Maybe we could change the weights so that error would have been 0. And then we take a new day and we make a prediction, and maybe now the error is 30, and now we adjust the weights somehow, and maybe the error is again 0 for the, so we keep doing this. Each time we run through a new example in our data, like a new day or a new flower, if we're talking about irises, and we get an error, then we want to adjust the weights. The weights are the things that we're going to adjust to improve the predictions. The question is how? How do we adjust the weights intelligently to get good predictions? So that's why we needed to review the concept of calculus, because that is going to be the trick that works. Now, people didn't know to use that calculus theory that we were talking about. They were just faced with this problem. How should we change the weights? And for 25 or 30 years, they were just coming up with lots of different ideas and maybe just trying it by hand. At first, they were just saying, okay, well, if we change the weight manually like this, maybe next time it'll be better, and maybe it'll be better, and we keep doing that. They didn't have any theory. But after about 20 or 30 years of thinking about this, they came up with a theory that involved using some of that math that we talked about last week. So we'll go to that next time. So that's all for today.